All right, what are the equilibrium concentration of all the dissolved reactants and products when 0.50 molar hydrofluoric acid is dissolved in water? Kc is 3.5 times 10 to the minus 4 for this reaction, and we have a little hint here. Pure liquids are not included in the equilibrium constant expression, and so we'll knock out water from our ice table as we're going to put this together right here below our balanced equation. It is balanced, it's just HF dissolving into H plus and fluoride there. And so initial, we said that we had 0.50 hydrofluoric acid, and so that means initially we didn't have any H plus or fluoride. What we're going to see is there be a change where we're going to lose our balanced equations 1 to 1, so minus X HF, we're going to gain H plus and gain fluoride as that HF breaks up. So whatever was present initially, we stress the system. We have too much HF for our equilibrium, so it's going to react by changing minus X, lose something, and then add 1 to 1 our two products. So our equilibrium concentrations are going to be 0.50 minus X. That's molar. Each of these is molar. Minus X, and then 0 plus X molar, and then plus X molar there at equilibrium. Okay, so at this point, we want to determine the concentrations using the equilibrium constant expression. So Kc, we said, was 3.50 times 10 to the minus 4 for this reaction, and that's going to equal our products, H plus, fluoride over HF, all raised to the 1 because we don't have any coefficients in our balanced equation. All right, so let's go ahead and write in our values. So X times X, and then 0.50 minus X is going to be equal to 3.50 times 10 to the minus 4. Well, at this point, we can do things the shortcut way by observing our equilibrium constant is very small relative to our initial concentration. And so if 0.5 is 5 times 10 to the minus 1, okay, so there's 0.50. Our equilibrium constant is 0.123, and then 4 for the 3, 50. And so it's very small, by 3 sig figs or 2 sig figs here, 3 sig figs if we go all the way to the 5, smaller than our value for our initial concentration. And what that means is X is probably also pretty small. And so when we're saying here, when Kc is very small by greater than 2 digits, smaller than our initial concentration, greater by 2 digits than our initial concentration, we can ignore X. Because X is going to be very small relative to 0.5 as well. And so what that means, this is the place where we can ignore X in this expression when it's related to 0.5. We can ignore it up here. We're going to lose any chance of calculating our equation. I'm going to prove it to you by doing it both ways. So this is a shortcut, and again, your professor may not allow this shortcut, so this is up to you to determine that. But at this point, we can say X times X is X squared, and we can ignore X is equal to 0.5, and all of that equals 0.123, 3.5 times 10 to the minus 4. So if we say X squared equals, here, got to punch it in the calculator, 3.5 times 10 to the minus 4 times 0.5 is going to give us 0.00175. 0.00175. 0.00175 is going to give us 0.00175. 0.00175 is going to give us 0.0000175. 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 0.00175 is going So that's half. And then the square root of both sides. That's going to give us 0.013 molar as X, and that's the concentration of H+. That's the concentration of fluoride, and that's X. And so if we're thinking about what HF is, it's 0.50 minus X, or minus 0.013. And so 0.50 minus 0.013 gives us 0.49 molar for HF. Okay, so we've got three values here. We've solved the problem. Now, suppose we didn't take the shortcut, and suppose we didn't notice that the concentration of the initial concentration was very large relative to Kc. We could solve this by the quadratic equation as well. All right, so I'm going to work that out for us as well. And let's go ahead and back up a little bit to the point at where we took a shortcut. And actually, I'll leave that there just so that we have it for later. And what I'll do is I'll duplicate it here so that we can see later. We can come back and compare the two. If I can get this wrapped around, there we go. Okay, and we'll come down here and we'll restart the calculation. All right, so this is where we got to when we set up our equilibrium constant expression. We had plus X for H plus and F minus. We had 0.5 minus X for HF, and we're not going to do any shortcuts. At this point, we're going to multiply both sides by 0.5 minus X. So X squared equals 3.50 times 10 to the minus 4 multiplied by 0.50 minus X. Okay, so at this point, we are going to distribute through our values, and we'll say that X squared equals, we're going to say 3.50 times 10 to the minus 4 times X. We'll subtract that, and then we'll say 3.50 times 10 to the minus 4 times 0.5 is going to give us 1.75 times 10 to the minus 4. So we distributed through this constant, 3.50 times 10 to the minus 4 times 0.5. That's where this comes from. Same number times minus X, and that's what we get here. All right, so we're all here. Now, to solve a quadratic equation, we've got to set that equal to 0 and subtract our constant from the left, add our X term times 10 to the minus 4. Make sure, see that better. And then finally subtract away our constant so that we set it up equal to 0. Now, ax squared plus bx plus c goes into the quadratic equation. So there's c, our constant. Let's change the colors there and put it all the same color just to make sure. So there's b, okay, right there. And so we're going to plug that in to the quadratic formula. And that's going to say that x is equal to negative b plus or minus the square root of b squared minus 4ac, all of that over 2 times a. All right, and so if we plug that in, our quadratic equation, negative b, negative 3.50 times 10 to the minus 4 plus or minus square root of that same number squared, 3.50 times 10 to the minus 4 squared, minus 4 times a, which is 1, times c, which is 1.75 times 10 to the minus 4. all of that over 2 times 1 is 2. Okay, so that's our algebra plug-in. Now it's a matter of getting it all into the calculator without making a mistake. So I'm going to do this a little bit at a time so you can kind of check yourself along the way. I've worked it ahead to speed us up here. No, we're still dragging around a little bit, but we'll speed up a little bit. I'll multiply that out, get 1.23 times 10 to the minus 7. When we square up here, minus 4 times A times C is 0.1237. All that under, and that's, again, we're going to be adding because that's a negative right there. Sorry about that. Missed that a second ago. See how easy it is when you're carrying it over. That term is negative in this expression because we are plus in the generic one, all right, the one we're guiding ourselves by. So this constant is negative 1.75 times 10 to the minus 4. Okay, so throw that in there. Now it ends up being a plus underneath our square root, then times 2. All right, so combine the terms one more time. We're going to keep out front the same until we get our square roots done. So plus or minus the root of, okay, we're going to calculate that out to 0.02645. 98, keeping everything in the calculator as long as we can before rounding. And so then we have to say, okay, well, what's going to happen here? We're not going to have a value for our solution where we're going to end up having x being less than our initial value. All right, so we don't want to end up with a value that's less, and so we're going to end up getting rid of our negative version. We're always going to do the plus here. Okay, just the way it works out, that plus or minus gives us two solutions for x. Well, we can't have both, and so what we don't want to end up with is having a value for x that's negative. Okay, so the smaller value will go away, and so we're going to leave it with plus. Well, at that point, we could add all this together, we could divide out, we get the same exact thing to two significant figures, that x equals 0.013 molar, and we get the exact same thing when we subtract out for HF. X comes out to be exactly the same when we do it by the quadratic equation versus when we do it by rounding off because it's smaller. Now, if the initial concentration is not smaller by 2 or more digits than our initial concentration, you can't do the shortcut anyway, and you have to use the quadratic equation or use the full algebraic method. Here we were fortunate enough to where we could do that, but if we didn't, we could still work it out from the beginning using our quadratic equation. Multiply all the terms out, get it set up related to ax squared plus bx plus c, then plug and chug from there on in our calculator. Again, being careful with this negative here, and the negative that was attached to our exponent, or excuse me, to our constant here, could have been a negative here, and so we wanted to make sure we get that taken care of. We also want to make sure that we take the larger of the two, the plus, not the plus minus that we get in the quadratic equation. Always take the plus so that we get our real answer and not just something that solves the equation, something that makes sense in physics and chemistry to be greater than that initial concentration. No negative molarities coming out in the end is what we don't want to see. All right, so there we have it. We're good to go. And we have our final answer, 0.013 molar for x, just like we had before. That's equal to the fluoride and hydronium concentration, 0.5, minus that gives us 0.49. Same answer if we do it either way.